I was told to talk about machine learning and computational imaging. Not quite sure I'm the best person to do that, but I'll try my best. So before that, this is in collaboration. A lot of the stuff I will talk about is in collaboration with a bunch of people. First off is Zalon, like post-PhD in my group. He's been leading most of this effort, including most of the slides you will see today. And he's going to be around as part of this program, so feel free to talk to him, ask questions, and so on. So, a lot of some of the work I will present is also joint from our own group. It's joint with Reinhard Heckel, who is a colleague at TUM, and Berk is also another student involved in some of these projects, a new addition to the group. Other folks that I've worked on, and I'll talk about some of their work too, who've taught me a lot about, in particular, the phaseless imaging side, phase retrieval. It's like Laura Waller at UC Berkeley and Lee Tian, so I thought I should give them a shout out during this. So let me begin with a motivation, right? The motivation is, of course, modern learning AI algorithms, whatever you want to call them, have been extremely successful in a bunch of different applications, right? Like, whether it's like beating humans at Go. More recently, this is actually the more scientific one, right? For protein folding, even competitive programming. A lot of these successes, in particular in natural language processing and vision, right? One commonality, maybe with the exception of the AlphaFold thing, is that, and I might get into trouble for saying this, right? But they're sort of more for internet applications, right? Or more in controlled environments in some sense, right? Again, the only exception here might be the protein folding one, which is more of a scientific application. So, whereas, I guess what we're more interested in this program is machine learning or AI for computational imaging, maybe even more broadly scientific applications. So in these areas, there's also a lot of opportunities for using machine learning and AI and so on. So one cartoon picture that I typically have in mind is like, you have some sort of sensing devices in most of the sciences, right? And you get some sort of image out of this, right? If you're not happy with the quality of your image, you typically go buy a fancier, more expensive device, right? So if you don't like your microscope, you go buy a more expensive one, you build a larger telescope and so on, and then you get the quality of reconstruction that you're after, right? And now, I guess the promise, at least, of machine learning in this context is, what if you don't need to do that, right? What if you can keep your cheaper, low-quality device, right? But augmented, maybe make some adjustments in hardware, right? Maybe add some coded diffraction pattern, something, right? A modulator of some sort, make the lens adaptive or something like that. But then augmented with powerful computational algorithms, I guess these days is more in the form of AI machine learning. And maybe out of the low quality device, you can actually get sufficiently good signal or measurements and so on, right? And so that's at least the promise, right, of using AI and machine learning in this context. Of course, there are challenges. There's a lot of challenges that is worth reminding you at the beginning. I will not be talking about how to address these challenges, maybe toward the end a little bit, but I want to throw them out there. So these you can think of as challenges and open directions, right, for future research. So there's, of course, the reliability challenge. I think Diana even was mentioning a few of these, right? So in the context of general machine learning, for a second, let me mention a few of them. There's, of course, a lot of examples of really bad failure modes of these stuff, right? So one famous example was like Microsoft put out like a Twitter bot a few years ago where it was supposed to be friends to humans. It became racist under 24 hours, right? So they had to shut that down. The Tesla released this fully autonomous vehicle, right? Or fully autonomous driving mode. Let's just say the reviews were not stellar, right? And many, many other examples that you're probably more familiar with. So this is more broadly in even those internet, like the mainstream AI applications, you see these issues. In scientific applications, it gets even more tricky, right? So for example, in medical imaging, you could have hallucinations, right? So here's an example of really a realistic algorithm creating hallucinations, in particular if you do not have a lot of training data. What we've done here is like if you train using 10% or even 1% of the training data, like these deep learning models, what you can see is that at least if you don't do anything to fix it, there are, I mean, it's not very visible here, but there are actually diagnostically significant detail that gets added, right? So there are actually, the algorithm is hallucinating things that it shouldn't be hallucinating, right? And not only is it doing that, in this case, they are diagnostically significant, right? So this is obviously going to be a problem when using these techniques. So these are some of the challenges. And again, it could really lead to misdiagnostic in this case. So I think these are some sort of tears, I'm not an MSK radiologist, but this is like some sort of tear or something of that form. So here's another example, maybe from nanoscale imaging, like let's say you're interested in imaging electronic chips or something. Here, it might actually hallucinate a part of the chip that isn't there, right? Just because, again, maybe you don't have enough data. You're reading too much into the power of these algorithms. Another fun one, I think this was a big deal on Twitter, right? Is so this is like an example of a super resolution algorithm, right? This is where basically, you want to go from the pixelated image to the truth, right? And so this is the algorithm used in this case is Pulse. This is the original picture. Clearly, we see that this is a picture of Obama, right? And then so once it imputes the missing detail, somehow Obama becomes white, right? Just the point of this is actually consistent with the data, right? So if you actually downsample this image, you do actually get this, right? So it's consistent, but it's hallucinating the detail, but it's hallucinating it in a white fashion, right? So clearly these algorithms have a bunch of bias in them. Yes? Yeah. So I might have like made a mistake when copying, but so yeah. Well, there's a debate about that, right? Which is like, I'm talking about the more pipeline in general. Maybe I shouldn't have said algorithm, but there's even a debate about that. I'm also a little bit more on the side that the data is biased, but there are people that think even the algorithm, the way you construct the algorithm is biased, right? Yeah. Other questions? Yeah, and keep the questions coming. I have a lot of slides, but we can stop whenever. So yeah, that's one challenge we should be mindful of, because I'll show you some success stories and review some of the algorithms, but these are challenges that we should be mindful of. Another thing that I think is very important is like this issue of like data scarcity, right? And it's well known that deep learning is very data hungry. And it's not as much of a problem as in internet applications, right? In some sense, like with NLP, computer vision, because, like if you think about the data acquisition, data is readily available, right? Like you have lots of images on the internet, YouTube videos and so on. You can look at the entire Wikipedia for NLP, stuff like that, right? So that's easy. Cost is typically very low, right? Again, most of the data on the internet is free. And even annotation, you can kind of hire Amazon Text to do that, right? So it's not that expensive, right? So you do not need very expert annotators in some sense, right? Obviously the amount of data is huge, right? Because it's the internet. So, but if you contrast that with scientific data, right? It's very different, right? If you think about a typical scientific pipeline, right? So there is some real phenomena you're trying to understand, image, whatever. So you typically have a sensor making those measurements, and then you get some data point, right? You repeat this process a bunch of times, and that's how you get a data set, I guess, in the more scientific applications. And then you have some sort of reconstruction or whatever algorithm on top, right? So if you think about it, in all parts of this pipeline, actually, it's a bit more challenging compared to the internet data, right? In data acquisition, in particular in scientific applications, can be extremely slow because maybe you have to calibrate the device, all of that, right? And typically, in some cases, it could be costly, right? Like this morning, John was mentioning like these are billion-dollar devices or whatever, right? So it could be very costly to gather this data. And then, again, data collection, even collecting it in the form of the data, right? Again, costly acquisition. One thing is, especially when humans are involved, it could also be harmful acquisition, right? Like you might not want to image a person too long, with especially, let's say, in the X-ray regime or whatever, right? So there's that issue. There might be some rare occurrences that you care about, which makes it even more difficult because, it limits your, you might need to even measure longer and longer to be able to detect rare occurrences. So yeah, there's a lot of issues of that kind that you do not face in internet scale data. And, even the algorithmic part, to be honest, it was even mentioned during the commentary of the last talk, right, that the data sets you have in scientific applications, you might have fewer of them, but they're actually very large scale, right? So the data set that you do have, like the total number might be few, but each individual data is actually much more high dimensional typically, right? So, and there's a lot of pre-processing, heavy computation involved. So the entire pipeline, right, is kind of more complex, right? And data scarcity kind of affects the entire pipeline. So some simple case studies, like for example, if you look at nanoscale application, if you're really trying to image things as, as fine grained as electronic chips, the data acquisition could take very long time. I remember we had this IRPA project a few years ago where, the calculation was if you want to do a basically image at the level of resolution they were interested, a 1 centimeter cube volume, it might take you 2,500 days, right? So it can be very slow. Cost is obviously very high. Again, calibration, even the devices involved could be very high. So the cost is quite expensive. And amount of data is low, though, right? Because, again, you have to calibrate this. They're expensive things. You cannot gather a lot of data, right? So unlike the internet scale, you don't have a lot of data. Another maybe example that highlights some of the other challenges one might face is let's say medical imaging. Data acquisition here could be slow, right? You might have to stick the patient in the MR scanner for a very long time, right, to get high quality measurements. And in some cases, it could also be harmful to measure a human for a very long time, right? So the data acquisition, there is these challenges. Cost, again, is relatively speaking high. For example, magnetic resonance imaging is not that cheap of an imaging modality. It's quite expensive. And then amount of data, again, if you look at publicly available data set, because there's all sorts of personal issues that you have to take into account and confidentiality issues. There are not actually that many large-scale public data sets in this domain, right? So this also creates another issue. Of course, there is also a computational complexity challenge that I think is much richer in scientific data. One issue is that typically the kind of, let's say even images, the images you see on the internet, they're much lower resolution. In scientific applications, you actually care about much higher resolutions. I mean, this is just comparing the data sets, typical data sets in something like ImageNet or CFAR, I guess in this case, and the publicly available medical imaging, right? Typically there's also the dimensions are much larger. There's multiple channels. In a internet data imaging, maybe you have RGB colors, but in scientific data, for example, in medical imaging, you might have 16 coils, right? So even in that sense, it's more complex, right? Another example is you might have both magnitude and phase, right? So typically scientific data, I would argue, is more complicated than the kind of data sets you might encounter on the internet. This was kind of an overview of the challenges. And since this is supposed to be a computational imaging meets machine learning tutorial, I should make a disclaimer, which is there's really a lot of exciting stuff happening at the interface between computational imaging and machine learning. I would argue even more broadly in the sciences, right? People are building this 3D cameras, right? Motion synthesis, right? This is stuff like NERF and so on, right? View synthesis. I was at this meeting the other day where people are resolving atomic structures of molecules, right? So there's really a lot of things happening in graphics and so on. Again, in the broader scientific applications, there's really a lot of exciting stuff going on. But this tutorial is not going to be about that. It's about a very narrow set of tools, which is basically deep learning for inverse problems, right? So I'll be just focusing on that. But I did want to mention there's really a much larger use cases and techniques that people are working on, right? But I guess this is more on my expertise, so that's why I'll restrict it to that. Let's do a brief introduction into inverse problems. Already many of it has been mentioned, right? But just give some examples of the kind of problems we're looking at, right? So in inverse problems, like this is typically the formulation. There is some sort of measurements, right, from some signal. So there's always a forward operator. It could be potentially nonlinear, including a lot of the things we saw this morning. And then there is some ground truth signal that we really want to recover. And also, obviously, there's in practice, there's often a lot of noise. So, if it's a linear, like a substantial number of these problems could be just linear, right? Where then the mapping would be just a linear mapping. And in these cases, at least over the last decade, the problems of interest has been situations where you have fewer measurements than unknowns, sort of in this compressive sensing scenarios. In which case, you could have infinitely many solutions, but with proper regularization, maybe you can still identify a good answer. So common inverse problems, probably the most famous ones is like denoising, right? Where you just have a noisy image, you want to denoise, and if you give a talk at IPAM and you talk about image denoising, you have to put Stan's picture on there, right? So it's a requirement, so I did that. So the common example is the image denoising. So another example, and these inverse problems that I'm talking about, the techniques are applicable to all of these examples. So that's why I'm briefly going over some of them. Another example is like just simple deconvolution. It could be that you know the kernel or you don't, right? Both of them. So if you know the kernel, it's kind of a linear inverse problem. But if you don't, then it kind of becomes blind deconvolution, and it's more nonlinear. It's kind of more quadratic looking. So basically, though, the goal is like you have a blurry image. You want to go to the clean, nice looking image, right? So another class. So another example that is quite popular is like impaling, right? Like if you have an image, part of it is damaged in some way, you want to impute the missing parts. So this would be a case of a linear version where basically some of the pixels are missing, right? A lot of the techniques in this space are actually, started from this kind of problem. So that's why we're mentioning these. A large class of them, at least in the theory world, right, are based on these compressed sensing models, where typically you have a sparse signal, you get very few measurements, often random in some way, for example, Gaussian, DFT plus random sign, from a sparse signal, and then you want to find the sparse signal from these measurements. This class at least has very nice theoretical guarantees and good algorithms, right? And often they explore sparsity in some sort of transformation domain, right? And a special case of this is MR reconstruction, where you could imagine that the image is somewhat sparse, or at least low TV in like an appropriate basis. In fact, it's the next example, right? In this case, it's a linear measurement where, real MR imaging is a little bit more complicated than that, which is like typically you have some ground truth of the anatomy that you're measuring. Then you have multiple coil sensitivities that are doing the measurements. And after that, you get to see the Fourier transform, because the MR imaging, you see things in K-space, but you don't see the entire K-space, but subsampling of it, right? And the reason for that is that you do not want to stick the patient in the magnet for a very long time. So that's why you have to subsample like this Fourier domain. There's coil sensitivities, then there is Fourier transform, and then you get a bunch of measurements like this. So this is another class. Tomography was mentioned, right? Computational tomography. Some problems of this kind, you can just model them as a linear transformation, where the linear transformation is just radon, right? And again, here you subsample because, as was mentioned today, you don't want to do all of the views. Maybe you keep some of the views, right? And then this is why it becomes underdetermined in this space, right? Another class, another kind of like this, I already mentioned, gave you the White Obama controversy was for this kind of super resolution problem, right? Where maybe you have a you have a low resolution version of the image and you want to go to the high resolution version, right? This you can kind of think of like a little bit subsampling in some sort of alternative domain, for example, the Fourier domain. So at least some of these problems you can model as linear, right? Where it's a product of a subsampling matrix plus a blaring linear operation, right? So that's for example, B here is like convolving with a Blair kernel, right? So this also fits the linear inverse problem model. And I guess we're getting to the end of this list. This problem was featured very much this morning, like maybe a good example of a nonlinear version of this problem, where it's like phase retrieval. You have kind of some sort of forward linear map, usually Fourier transform or oversampled Fourier transform, as we saw this morning, and then you get magnitude measurements or magnitude square measurements because that's what devices measure. They measure intensity. And so the goal here is to recover, in some sense, phase information from magnitude-only things. A, as John mentioned this morning, is often some sort of DFT matrix, oversampled DFT. If you're clever, or you're using tychography or other measurement apparatus, it becomes like DFT matrix modulated in some way, right? Either by putting a faceplate before the sample, right? So here you might put a faceplate, then in a far field you get the Fourier transform. On the screen you get to see magnitude measurements. This is how you end up with this equation. Or in tychography is kind of similar. You don't actually have this particular faceplate, but essentially you end up with a similar formulation. So this is another class of things that you could cover using this inverse problems. But how do we solve it? So it's good to go very briefly over the history so that we can finally end with like machine learning ways of solving these inverse problems, right? So the simplest way that they did it historically was, if you have a kind of a linear inverse problem, right? Even if you have more unknowns than measurements, of course the issue is that there is no unique solution. But like the first things people did back in the day is kind of like filter the back projection or something, right? Is you try to find the least norm solution, right? So kind of like just pseudo inverse A, and you hope that that's good enough. So that's like the first simplistic approach to this. And of course, then over the last decade, in more of these compressed sensing areas, there was this idea of, can we do better by leveraging side information, right? Like if we know something about the class of signals that we're trying to reconstruct, maybe they're sparse in some domain, right? Can we utilize that to do better, right? And this kind of led us to these kinds of formulations, right? Where you can call it compressive sensing formulations, where you kind of have a data consistency term, right? Which basically enforces that the forward model matches the measurements. And then you have some sort of regularizer that enforces the prior knowledge that you have about the underlying signal. So often in this literature, this regularizer was some sort of sparsity or low TV norm in an appropriate basis, like a Fourier basis, maybe an overcomplete wavelet or something like that, right? And the way you would solve these things is like, you formulate this optimization problem, you run an iterative algorithm typically to find the solution, right? But now, more recently, people are approaching this in a more data-driven fashion, which is, can we also, in some sense, learn the regularizer from the data, right? So, somehow like capture the side information directly if we have a collection of data of a particular kind, right? And so for example, like in let's say in imaging, in this case medical imaging, what if we have a bunch of paired data where like the like the case-based data, which is or the response, and the actual medical image we're trying to reconstruct, right? If you have a collection of data like this, can be all in an data-driven fashion, right? Like also build the regularizer and do the reconstruction all simultaneously, maybe. There are a little bit even fancier versions of this problem that you could think about, and people have thought about this. It's kind of in an unsupervised inversion. So this one is supervised because you have your data set contains both a pair of signals and the corresponding measurements, but you could even have cases where you don't know which measurement corresponds to which signal, right? So you might have a collection of signals and measurements, but you may not even know the pairing between them, right? So there are techniques for that. We will not really talk about these two, but maybe a little bit the second one. Or it could be that maybe even the measurement is gone. You just have the signal, right? But still, you might be able to leverage this unlabeled data or partially labeled data to build your regularizers, right? But we mostly will focus on that. But I do want to mention that there are techniques even in this case, right? Even if you don't know the pairing, sometimes you can. There are algorithms in this area to deal with these issues. So in the supervised data-driven kinds, there are kind of two paradigms emerging, right? Really three, but let's first focus on the first two. So one paradigm is based on generative models, and this is just the outline. I'll jump into them, right? So these are techniques where you're trying to essentially learn the distribution of the underlying data, right? These are based on generative models. So using using a bunch of data from the input domain, right? What you try to do is try to learn a latent representation for this, like and then given a new measurement, you'll try to adjust the input to match the measurements. This is very vague. I'll give you more detail in a second. But one class of techniques is based on these, build a generative model to model your data and then use this in the reconstruction process, right? So in some sense, in this technique, you're kind of learning, a kind of latent representation of your input data. A second class of techniques is like completely end-to-end method, right? In these end-to-end methods, you have a bunch of training data, which consists of like the things you're trying to image or your signals and the corresponding measurements. And you try to directly go from the measurements to the signal, right? So you basically try to build networks that, given the measurements as input, spits out an estimate of the signal that you care about, right? So this is completely end-to-end, right? So there's no intermediate way of representing the signal or whatever. Give me a new measurement. I just pass it through this network. I get my ideal signal that I'm interested in, right? So I'll talk about these two techniques now. So are there any questions or commentary or anything? Go ahead.
I don't want to be offensive in asking my question because it's a little bit controversial, but like when you, for instance, let's say MRI data, we decide in this room that, for instance, the images are sparse.
Yeah.
And we decide that a very convenient way to make, beautiful images is to add a regularizer. And then this action that we take today is going to go into like medical devices, going to be sourced to the next generation of doctors, and then they're going to use those machines. And then let's say, hypothetically, there's a new condition that we're trying to diagnose that will appear in the form of a non-sparse variation on normal.
Right.
In which case, like the technique we have right now, by that assumption, would probably, either erase, if not faint, make this feature faint. So aren't we, in a sense, in an effort to provide images that are denoised and beautiful, somehow cornering ourselves into a reductive way of enabling diagnosis in medical imaging? And my question is really, how can we get out of that loophole and ensure that we're not ditching any data by making prior assumptions too drastically or too early? What are the safeguards to prevent that from?
Yeah, I think this is like kind of an open question, but it's a very interesting one in this area. I do think that data-driven techniques are a little bit better, right? Because it says at least if the phenomena is present in the data that you've seen so far, the algorithm will utilize it. So whereas sparsity was a little bit more leap of faith because you're assuming that the data is sparse, right? And it might not be, right? But still, these suffer from the same issue because what if there is some phenomena that you have not seen? It's very rare. You have not seen in your training data at all. Obviously, the algorithm doesn't know what to do with that. I think a really interesting question, which to me actually I would love to have an answer to, and the pulse example with the white Obama picture highlights, right, is if the algorithms also spit out a notion of confidence, right, in a sense that say, oh, actually, with this measurement that you give me, I will not be able to be very certain about my reconstruction, right? Because, like the white Obama example shows, right? Like, the algorithm reconstructs and said, oh, this is the image, right? But if we had some notion of, I'm not really sure about my reconstruction, it would have been nicer.
But
right?
even that notion of confidence is depending on our understanding of what the data looks like. Because imagine I could input a picture of a high resolution Obama plus salt and pepper noise.
Right.
That would be the high resolution data. And even if the algorithm upsamples to like a clear picture of Obama, that's still not the reconstruction we're expecting. It's one that we're more likely to accept based on what we expect the machine to do.
Right.
But that also depends on the data. The confidence interval depends on what we find.
Yeah, I mean, absolutely. I think I think it mitigates the issue. Somehow, it doesn't make it go all the way away completely, right? So yeah, with prior knowledge, there is always a little bit of this leap of faith, unfortunately.
I don't want to derail your talk.
No, go ahead.
I want to add one piece of complexity, which is from these kinds of inverse solutions, as someone who does experiments, I would actually like two slightly different pieces of information about the quality of the reconstruction. One of them is what is the uncertainty in the estimated reconstruction? Mm-hmm. Meaning the data are not perfect, it has some noise or some variability. How does that variability translate into the parameters of the reconstruction? And then the other one is this question of domain. Is the reconstruction likely in domain or out of domain for the network? And I think those things need to be distinct because we should always get uncertainty. And there should be times when the network says, nope,
Yeah.
sorry, haven't seen this before, don't trust what I have to say to you, no matter what the size of the uncertainty is.
Yeah, so I agree with that. Like, again, with the Pulse and Obama picture, it should just say, no, I cannot do that, right? Like, in some sense, right? Because, there should be some safeguard saying, I do not have enough measurement, to do anything reasonable, right? And I think that is something that I think it is necessary in this area, right? Because you could keep going on lower and lower measurements and just hallucinating detail, right? And it might not be real, right? So absolutely, those are really interesting points. And hopefully we will get there at some point. So let me talk about these two different classes and like a little bit the history, what is out there, right? And maybe some of the drawbacks and and so on, right? So the first class is kind of these deep generative models for solving inverse problems, like very exciting, right? So let me begin by forget about using them in the context of inverse problems, right? So deep generative models, the real purpose is like essentially efficient modeling of high dimensional data, right? So here the idea is that, I want to learn a mapping that go from some simple seed input to actually complex high dimensional data that we see in our data sets, right? So in this case, most notably in this field often is like, I want to go from a Gaussian vector to a distribution that resembles the kind of data set that I'm interested in. So really generative models in their essence have been designed to somehow like go from noise to the realistic distribution, right? And of course, so there are some parameters that you play around with, right, to learn this mapping. And then, because you have some at least samples from the true distribution in the form of training data, you try to minimize some sort of loss, ensuring that that kind of like the distribution that comes out of this generative process in some sense matches the distribution of the data that you have, right? So really generative models, like in this case, of the deep kind, they're made to kind of learn the underlying distribution creating your data, right? So that's kind of the thing, right? Like, so really, given a Gaussian noise, ideally they go to like, in some sense, learn the manifold of images or signals or whatever, right? So you get a naturalistic looking image out of this, right? Once it's been trained on a data set, right? And so ideally, if you input different Gaussian noise, you always get natural looking images, right? So that's kind of the idea. So over the years, these deep generative models have evolved and they really produce very nice images, right? But here's a kind of a history of this. It started more or less with variational autoencoders, right? And we should have actually put the quality of the images where you would see how it has really improved, right? And then, the second kind of act was generative adversarial networks or GANs, right? More recently, things have kind of shifted toward using normalized flow models or diffusion models, right? These are the same kind of techniques that appear also in DALL-E 2 and stuff like that, right? So historically, this is how they've evolved, and really, like, they produce very high quality images from Gaussian noise at this point, right? So they're very fascinating. But how do you use it in the context of inverse problems? So here, I'll focus just on linear inverse problems, but the same machinery works, right? So you could use it for nonlinear inverse problems, right? So what you would do is like essentially using your input training data. If you have a collection of your input training data, what you could do is try to learn a generator that kind of learns the distribution of your input, right? So using a loss like this, so ZIs are different Gaussian inputs, right? You try to find a parameter that kind of like learns the empirical distribution of your data at least, right? So these are your input data. Once you learn this generator, right? So then you could say, okay, using the parameters of the learned generator, if I have a new measurement, now I'll try to play around with the latent representation of the data. So this is no longer Gaussian noise, but you actually minimize over it. So this is kind of supposed to be a representation of your model, right? So then you take measurements from this representation. You apply the forward map. In this case, it's linear, but even if it was nonlinear, you do the same. And you try to find the latent representation that is consistent with your measurement, right? So in some sense, you've learned, the manifold or whatever you want to call it of the where the data lies in from your training data, and then you just try to enforce that in your forward model, right? So you minimize the latent. You try to find the latent parameters that fit this model, right? Go ahead.
In this case, is the encoder network fixed, or do you train that as well?
I think so during the training you do both, right? You do both, but here in the next in kind of test time, right? So during the training phase you train everything, but at test time you're now fixing the parameter theta. You're just optimizing over the latent representation. Yeah. Any other questions or comments? So yeah, you try to find the latent representation that matches the measurements essentially. So this kind of technique actually does work better than sparsity-based priors for a lot of the inverse problems that we've discussed, right? So it actually does, it's kind of a data-driven way to find your latent representation, right? So it actually, like, for example, for a lot of these problems that we discussed, it might allow the same reconstruction quality with maybe a factor 5 to 10 less measurements, right? So in that sense, in some sense, these techniques are working. And I have some of the references here, but it's getting cut. So this particular one is from Alex Demarcus's group. So here's another example where I think this is by Paul Hand and Vlad Warninsky, right? Like they've used it for even a phase retrieval model. Like imagine you have a phase retrieval model on top of an MNIST looking data set, right? And they've compared, using these priors compared to not using priors at all, right? Like some of the more FineApp kind of GS kind of algorithms without priors, and even with, I think some of them are with sparsity priors. You can see that these kind of techniques allow you to achieve higher reconstruction quality with fewer measurements, right? So in that sense, it does seem like they're capturing prior knowledge in your data set in a finer manner, right? But one thing that you already see with these generative models, somehow you get the best, best utility out of them when you have very few observations, right? And this is unfortunately a pattern that you will see often in generative models, right? Their performance kind of stagnates, sometimes even becomes worse than sparsity priors when you have lots of measurements, right? So this is kind of a somewhat of an established issue in this area. They kind of hit an error floor, right? So if you have a lots and lots of measurements, they typically don't yield as good as a result as you would like. So they're really better in situations where you have very few measurements. So they do hit kind of a bottleneck. This error floor keeps decreasing as you use better generative models, right? Like remember the sequence going from variational autoencoders to GANs and so on, right? All the way to diffusion models, but somehow it seems to be there, and so that's kind of one of the issues that generative models seem to face. So this is a use of these kind of techniques in blind deconvolution. Again, seems to work pretty well. So this is, here's a reference for that. So this is, in particular, this is the one with the white Obama controversy, right? This is what it produces really nice images. Like this is a technique known as pulse, right? Using generative models for super resolution. So really, like this is from very low resolution image, you get very high quality reconstructions, which are really consistent with your measurements, right? So it is doing what it's supposed to do. Of course, as we discussed, it might be also having some biases in the training data, right? But at least it solves the problem, right? It gives you a solution consistent with data, and it's very high quality, right? Bias issues aside. So in this case, basically you have the linear model and you use a generated prior as a model for your inputs. So in this case, the generator is like by this generator, which is known as style GAN, which is trained on your input data. Okay, so but really, again, I want to highlight like the existing barrier to using these kind of deep generative models in inverse problems is this kind of error floor, right? That somehow, even compared to traditional sparsity-based methods, their reconstruction quality stagnates when you have very large measurements, right? So they always seem to hit this error floor. Maybe at some point, people come up with even richer generative models where this error floor is so small that you can ignore it. But for now, we seem to hit this error floor. So that is kind of one issue with these deep generative models. Go ahead.
So I'm just wondering if you ever run into optimization issues in the second step where you've like basically taken a convex in your problem and made it like super nonlinear, super convex, maybe not even differentiable. Is that ever an issue?
Always. so with these GAN models, this is always an issue, right? Like even on the training data, GANs are very finicky. You have to be very careful about how you train them. Sometimes you have to stop early. You cannot just train them forever. There's all sorts of issues with that, right? We in our group, we actually don't use these techniques a lot, so I personally haven't experienced them, but I've heard a lot of horror stories, basically. So it is a tricky business. Like training GANs is not easy. Yeah.
Is there any non-relationship between the lower bound on the error and the size of the network?
Theoretically, there is none, but yeah, I think it is clear that if you had a much larger data set and you could, at least, I think there's even some experiments like this where if you in principle, if you have larger and larger data sets and you could train larger and larger GANs, maybe this error floor would go down, right? So at least, it's a folklore statement, right? Empirical one, but I don't think there's an actual theorem characterizing this issue. Yeah. Very good question. So in principle, it could be that we just need more training data and then the performance of the GANs become better. But again, the issue is in scientific applications, we might not have that much training data. Very good questions. Any other questions? Go ahead.
Is it often the case that the latent variable that you call Z is very low dimensional?
Yeah, somewhat. It's often of a lower dimension, yeah. Actually, Zalan, do you know what the dimensions are or no?
At least 10 times less than the...
Sorry, what?
It's at least a factor of 10 times less.
Smaller?
Yes.
Yeah, okay, cool. Other questions? Go ahead.
Is there an optimal way to choose the dimensionality of the latent space?
No, I think everything is a hyperparameter here. I think they have some understanding of what to do, but not very precise ones. So this gets us to the second class of techniques, which is like end-to-end methods, right? Somehow these don't seem to face the same error flow. So that's why, to be honest, I personally were very skeptical about these end-to-end methods, but I've become a believer, so for what it's worth. And it is kind of crazy, right? Because, you're saying like, I just get a bunch of training data of the form input, output, right? And I'll just try to directly learn a mapping that goes from measurement to reconstruction, right? It's end-to-end, right? So that's the idea here. So, for example, if you want to solve a noisy inverse problem, right? Whether linear or nonlinear, you really just have a bunch of, here is for denoising, right? You have like the ground truth image, a bunch of training data, which is image plus noise, right? Imagine you have a bunch of training data like this, and then you really just try to find a network that on the training data at least denoises all of the images, right? So usually, you go from the response or the output measurement, whatever you want to call it, you pass it through a neural network, and you make it consistent empirically across all your training data with the corresponding ground truth, right? It's really that kind of formulation. So these are end-to-end methods. And, again, at least on a lot of these inverse problems, this is like a public data set on MR. This is the fast MR public data set. It's used for accelerated MR imaging. You see all the top performing techniques, they're end-to-end. So these are the techniques that seem to be working very well in this space, at least on this public data sets. So the first network of this kind was the UNet, right? So this is like I believe one of the first networks used to do this. So you already see a lot of, a lot of components that appear in a lot of traditional signal processing, right? So there is usually a convolutional blocks, right? Which is very natural, I guess, in this domain. Then there is a bunch of spatial downsampling in the UNet, right? This is why it's U, right? So there is downsampling. Then here is kind of where you get the latent representation in some sense. Then you have spatial upsampling and then another set of convolutional blocks, right? So that this is hence the name U, right? So these are UNets. Now, I guess the next big development in this area was like to use unrolled networks, right? And I mean, the way I think about unrolling is like basically iterative denoising. So I thought maybe it's good to do a slight detour, right? Which is, I call it from denoising to compressive sensing, right? And there was a really nice literature, and I'll mention some of the interesting work, including, I believe, some people in the audience, right? That did all of these things. But this is how I at least think of unrolling, and so I thought you might also appreciate this, right? So, going back to the compressive sensing days, right? So if you want to do a sparse reconstruction from a few measurements, algorithmically, what would you do? What you would do is like basically you do a gradient update on the least squares loss. It looks something like this. and then you pass it through sort of a thresholding function to enforce sparsity, right? So usually like soft thresholding, hard thresholding, stuff like that, right? So you do a data update based on consistency with your measurements, then you do some sort of thresholding to enforce your prior, right? In this case, sparsity. And so this is what a video of that looks like. Like as you iterate, you denoise in some sense more and more, and you end up with, the sparse solution is kind of like, iterative denoising. So, and really the way I think about it, what is so special about soft thresholding is that it's a good denoiser for the class of priors, in this case sparsity, that you're interested in, right? So you can think of each iteration, and this is actually the thought process in some of the earlier compressive sensing work, right? Which is like, you have a noisy, because of the measurements or undersampling in the measurements, you have a noisy signal in each iteration and you're trying to denoise it. So this is why you do soft thresholding, right? So really, like intuitively, you can think of like better denoiser kind of translates to better thresholding function that enforces your prior. And so now you might ask, okay, what if my prior is not sparsity but some sort of natural image, right? It still works, right? So imagine you have a image like this, which is very rich. It's not clear in what domain it's sparse, maybe in wavelet, but you don't know, right? And then maybe let's say you have a few measurements from this natural image. You could actually, use any denoiser in this iterative reconstruction process, and it will yield good results. So one example of a denoiser, this is not a learned one, right? This is just a good denoiser. There's no learning involved. It's like in this context for natural images, it's CBM 3D, right? There's some denoiser that works pretty well. So if you, and let me just demonstrate that this is actually a good denoiser. So if I have a signal, I add Gaussian noise to it, and then I apply this CBM 3D3, right? You actually do denoise the image, right? So it is actually a good denoiser for natural images. So now if you employ this instead of like soft thresholding, you iterate with your measurements, but now you use this in every iteration. You can see that as you iterate, the reconstruction quality becomes better and better, right? And after like 100, 200 iteration, you actually reconstruct from this is with undersampling, right? You can actually reconstruct, right? There was no learning involved here. I just iteratively we apply denoisers, right? You take one gradient update in the least squares cost, and iteratively you apply this denoiser. In this case, a non-learned denoiser, right? It's a fixed denoiser. And so, in fact, there is a rich history of doing this in compressive sensing, right? Again, like we're at UCLA, so in the context of TV regularization, there's a lot of cool stuff at UCLA done, right? In the context of AMP, very nice work for the connecting denoising and compressive sensing. Theoretically, even there has been a lot of nice work, right? Like, for example, in the convex case, also local LA folk, right? Like people at Caltech, Christos, Summit, and Bobak showed that actually, there is a precise connection between undersampling and denoising, right? Better denoisers do mean better reconstruction algorithms. We also did some theoretical work with one of the co-authors there to basically extend this in a non-convex setting. So I want to say that this idea of using a general denoiser is somewhat well grounded even in theory, right? Now, where does the learning come in, right? You can kind of think of these unrolled network as, what if I also learn the denoiser, right? So that's kind of the idea. What if I also learn the denoiser, right? So let's say I want to do something like this. I have a regularizer, right? So I do a gradient update. There's a data consistency term, and then like the gradient of the regularizer. This you can think of sort of as your denoising operation. So I take a gradient update, and I also have a denoising operation. So the main idea behind these unrolled network is like, obviously I don't know what the regularizer is. What is the best denoising map? What if I try to directly learn that too, right? And in particular, why don't I model this denoiser as some sort of neural network, right? So this is what you end up with. You start from some initial guess. You have a data consistency term, right, coming out of the gradient. And then you have like a denoising term, in this case, a denoising network. But now what if I repeat this process, right? So, in the next iteration, I do this, right, and so on. But I stop at some point. Maybe I do, this is why it's called unrolling, right? And, maybe I say, like, I'm interested in stopping this after 10 iterations, which would correspond to a depth of 10, right? And then I try to train all of the parameters of all of these denoiser networks based on my training data. That's kind of the idea. So it's this unrolling, right? I'm trying to learn all, like all the 10 denoisers, right, directly from training data that I use in my reconstruction, right? So it's kind of like this is at least how I've managed to convince myself these are good ideas because of the connection to these denoising phenomena. So this was one idea, and this unrolling actually did really improve a lot of things. I do not have numbers here. But one important update, at least in the MR space, medical imaging space, was that people realized that if you do this unrolling in K-space or Fourier space, you get better quality, right? And so the next idea was that, okay, I'll try to do this unrolling in the Fourier domain, right? It seems like a harmless trick, but it actually did improve things quite a bit. So in the context of medical imaging, this allowed people to also do something, because in the context of medical imaging, there's additional components. You have multiple coils, so it's a little bit more complicated than that. You have to apply inverse Fourier, and then collect all of the multiple coils into one image, and then apply this denoiser, and then you go back. So in this context, one of the innovations of this work was, what if we also try to learn the coil sensitivity maps directly, right? So using some sort of another smaller neural network directly from the measurement data. So that was another kind of innovation here, which I imagine could this kind of thing also shows up in a lot of other imaging domains. So this was a major improvement actually, right? So in fact, this was like the top of the leaderboard in like this fast MR acquisition data set for 2 years or so. I guess, one question that we asked in our group was, can you do even better, right, if you use even more modern architectures? And so what we looked at was like, maybe can you do even better if you did the kind of denoising networks that you use maybe are of the transformer kind? So intuitively, some benefits of that is that, convolution is very content independent, right? So you could have a piece of bone here versus somewhere else. Convolution, because localized, does not appreciate that, right? Whereas transformer models are made for this kind of situation, right? As I said, also for long-range dependencies, again, convolutions are not ideal. So this is why we thought about using transformers, and so I won't go through the details of transformer models, but basically there is a self-attention mechanism and so on, right? So actually I'll skip the technical details of how we use transformers and what we did exactly, because Zalon is here. He might give a talk. We might talk about the details of this in a future workshop, right? So I'll tell you about that later, maybe, in the interest of time. But basically, there was a lot of innovation, but basically we managed to kind of get these transformer models to work for this space. And so I guess, but some of the tricks that I do want to mention is, which is very important, adding unrolling, as I said, is important. So even if you use transformers, fancier architectures, you should always unroll. Somehow this really improves things, right? So this unrolling trick is very important. Another important trick that I think works very well, at least in the context of MR domain, is like sometimes, especially if you have volumes, again, like in 3D reconstructions of like the kind of problems in phase retrieval that came up this morning, right? 3D phase retrieval problems, I imagine this would also show up. It's sometimes good to input like 3 adjacent slices and then combine that, like ask the network to reconstruct the middle one only, right? Construct the 3 of them and then combine them to get like each individual, image, right? So these kind of techniques, it seem harmless again, but actually boost the performance significantly. Like instead of asking the network to reconstruct each individual slice, ask it to reconstruct 3 adjacent slices, and then try to combine them, right? Like these kinds of ideas actually help a lot. So I do want to mention that these kind of techniques have also been used not only for medical image reconstruction, which is linear domain, right? But for example, in lensless imaging, I'm not, in this case, it's based on some sort of ADMM unrolling, right? I'm just giving them a shout out, so I'll share my slides so you can look into these in more detail. It has been also used. This, I think, is work by Laura Waller and her collaborators, right? Like they've been even used for designing the coded diffraction patterns, right? Like with the illumination patterns that you use, right? So this is the unrolling pipeline that they had. So you could also think about, like, you don't have to do this unrolling based on kind of gradient descent. You could think about other kinds of unrolling, right? Becca Willett and her collaborators, what they looked into is like kind of other kind of unrolling. For example, one thing they did is, like, based on these Newman series expansion, they naturally came up with skip connections that show up if you think about it as slightly different kinds of unrolling. They also, in another extreme, you can also think about it as what if I want to iterate to infinity, right? Not stop at a finite number of iterations. And in particular, what if I want to iterate a different number of times between training and test time, right? There are ways to do this using deep equilibrium architectures. The particular work I'm referencing here is, again, by Becca Willett's group, but there's also a lot of other activity in this area, including by Stan and his group at UCLA, and a lot of other exciting things, right? So yeah, like, this is kind of like just to give you an idea. Very briefly, I do want to mention another class of results. These don't perform as well, but I always find them very fascinating because they require no training data, right? It's very fascinating. So there are even untrained networks, right? Like, really networks that don't even have training data that also work in this space, right? So let me explain the concept using denoising, right? So the question is, like, I have a noisy image, can I denoise it, right? So these untrained networks, the way they work is, like, there is no training data. I just have the noisy image, and I want to get back the noiseless image, okay? So that's what I want to do. So in this context, you would have the noisy image. Then you have a network with some parameters. You set the input at random, and you just try to fit the parameters of the network to match the noisy image, right? You can imagine that this could go very wrong, right? Because you just have a single image, and if you pick a sufficiently large network, you can fit anything, right? Including the completely noisy image, right? But here's the surprise. If you stop this process early, you can actually, in many cases, you get a denoised image back, right? Which is very surprising. And here's a different view. Because this is a rich network, if you keep on iterating, you will eventually get the noisy image. You fit that perfectly. But if you stop somewhere in the middle, you actually end up getting the denoised image back, right? It's really surprising. This was kind of maybe popularized in this really fascinating paper called Deep Image Prior. They showed that using these, again, there's no training data involved. You can actually do various kinds of denoising, impeding, super resolution, and so on using these kind of techniques. Of course, there's no magic here. Somehow, the architecture of the network is somehow encoding the prior information, right? But the fact that it works without any training data, I think, is very fascinating, right? You can even use this kind of pipeline then in like an inverse problem, right? So because you could say, I just have like a kind of a network, right? I input Gaussian noise. I'll try to play around with the parameters to fit my kind of measurements, right? But sometimes I iterate forever. Sometimes you don't even need to. Sometimes you stop early. Sometimes you don't even need to stop early, especially if there's some random measurements. It still works, right? It's not something we fully understand, but it can be helpful if you have absolutely no training data, right? So somehow, again, the idea is that the regularizer is somehow implicit in the architecture of these networks, right? So this is an example, as I mentioned, for denoising and super resolution and stuff like that, right? Somehow the idea is that, clean images, you fit them kind of faster than you fit noisy images. So if you stop early, you fit to the signal, you don't fit to the noise. That's kind of the idea behind this. So that's why, at least for denoising, you should early stop. These kind of literature started with these deep image priors where they had like encoder and decoder architectures. Reinhard Reckel and I think Paul Hand realized that actually half of the network, this idea works even if you delete the encoder. So they came up with deep decoder. The advantages of this is like these networks were over-parameterized. These have much fewer parameters. And, we even in a subsequent paper realized that sometimes even it works with fixed convolutions. So you don't even need to, train the convolutional layers. You just need to train the coefficients. There's no training data, so just fit the coefficients, right? So it's very, interesting. I should also say that this even works in a compressed sensing context, right? If you have undersampling measurements, we could even prove some theorems about it, right? But let me show you some images, right? So this is vegetable MRI because back then we didn't have a lot of computational power, but you can see like you can do even compressed sensing. Subsequently, people actually tried this for medical imaging. It is not as good as end-to-end methods, right? Like the fancier kind, but it actually matches the performance of, it does as good of a job as like a TV regularizer or the simpler end-to-end methods like UNIT, right? It cannot do as well as like the fancier kind in medical imaging, but still the fact that without any training data you can get there is kind of, I think, impressive. This is work by Reinhard Reckel and his group, and this is an independent work by Mickey Lustig and his group at Berkeley, so this kind of technique also works, right? So, people have tried this again in the context of phase retrieval also with some success without any training data. Right. So in the interest of time, I'm just, go ahead. Yeah.
When you say you have to stop early, when do you know how to stop?
Yeah, so that's one of the issues, right? Like, so for compressive measurements, actually, it's not, because at least when you have randomized measurements, it's okay if you don't stop early. But for noisy reconstruction, you have to stop early, and that's the art part of this, right? Like you don't know where to stop, right? People have some heuristics, but that's one of the hyperparameters you have to tune, which is not very reliable, but So you can imagine though, that is, with a little bit of training data, you could tune that very well. So even if it's not fully untrained, because it's just one, early stopping parameter, hopefully you don't need that many training data to tune that, right? So, but yeah, it's definitely a big issue in this space, right? So I was going to tell you a little bit about how to reduce the data, but let me skip that and go directly to the challenges. We're happy to talk about some of these, techniques as the program progresses, right? But some future directions. I think all of the challenges I mentioned were already future directions, right? So, but just to highlight this, I think reiterating, robustness is a big issue in this space, right? Like these issues we really need to resolve. If we're going to, if this is going to be used in practice, I think we need to resolve these robustness issues. Because these are very rich, fancy models, right? They have a lot of hallucination power. So we have to somehow have some safeguards, as was also brought up in the questions, to make sure like it does not affect our reconstruction pipeline. I think, to me, reducing reliance on training data is very important when it gets to scientific applications, because, again, these are not internet scale problems. We cannot gather a lot of training data. It turns out, in the slide that I didn't show to you, it does turn out that reducing reliance in training data does, to some extent, deal with the robustness issues, right? In the sense that if you can train these things to work with less data, it often means that they're more robust because you kind of relied less on the training procedure, right, in some sense, right? And so we've investigated a bunch of different techniques to do this. We've had some limited success, but kind of the dream in the MR space, right, is this is where we are now, is can we get the same reconstruction quality with the 1% of the training data as if you have 100%, right? Because I think for scientific applications, this is a more realistic point to operate in. We haven't gotten there. Maybe in the MR domain, we're kind of like a factor 10 there. But the real question is, can we get 100% reduction in training data? Can we make these approaches work in that kind of regime? And I think that's really exciting. I also think there is really a lot of exciting applications. If we can make these deep inverse problems work reliably, there's a lot of exciting applications. One in the medical imaging domain, but I'm sure that I'm interested in. But I'm sure in the kind of stuff you do, there's also a lot of interesting test cases. Is, for example, it has to do with getting away with better, smaller devices. Like in the medical imaging domain, it is like, can we actually have high performance, low field MRI, right? And here the question is like, MR magnets are really hefty and large now. Can we get away with almost portable, small medical magnets, right? The advantage is obviously a lot. Like you would have portable stuff. They're much lower cost, right? Because maybe they're smaller magnets, right? They do not require as much space to operate. Sometimes hospitals have entire basements dedicated to their MR machines, right? And in the context of medical imaging, this is very useful because smaller magnets means lower magnetic fields, which means like maybe even if you have artifacts like metallic artifacts like metallic knees or even heart pacers or whatever, it might work with those, right? But of course, the cons are a lot, right? Exactly because you have lower magnetic fields, you do not have as high quality as the measurement. The contrast is different. You have a lot of noise, right? Like the SNR is much more limited and so on. But the real question is, can we computationally adjust for those issues, right? And get away with using the less expensive device. And I think in the context of even microscopy, a lot of other devices that are of interest in this program, I think you have similar situations, right? So there's a lot of potential, but the question is, can we do these translations in a reliable manner? And I think there's really a lot of at least exciting directions in that space, right? And more broadly, I was in a Packard Fellows meeting last week. Really, like the kind of things that are happening in the sciences more broadly is really exciting. I think there's a lot of opportunities, in the sciences more generally, right? This is not something I work on, but I think it's just like astounding the advances that are happening here. And one thing I want to mention, it's kind of interesting. The reverse may also be true, right? Which is like, there's also a lot of opportunities for using the sciences in AI, right? So some people believe that the next wave of GPUs might be optical in nature, right? Because if you think about it, like, optics can do Fourier transform much faster than existing GPUs, right? I was at like a DARPA PI meeting where people were talking about potentially, if they can figure out how to implement nonlinearity and calibrate it well, maybe the next wave of GPUs might be optical, right? So I think it's also sometimes good to think about the other question, which is like, can we use the sciences for accelerating AI or something like that, right? Because like a optical imaging pipeline kind of does convolutions. Maybe it even does some nonlinearity naturally. Can we do that to actually train these models faster than a computer does, right? I think the reverse is also quite exciting. Again, not something I'm very familiar with, but seems like an exciting direction. And so with that in mind, I said it's mandatory to kind of put a picture of Stan Osher when you're talking at IPAM. As a USC faculty, I'm also contractually obligated to advertise USC at UCLA, right? So we in fact, talking about AI for the sciences, we actually did start a center on building AI for the sciences at USC. And if you want to walk to the other school in the LA area, this is what it looks like. So we do have a bunch of postdoc positions and faculty positions available. So feel free to reach out if you're interested in that. And with that, let me end it here. Oh, and I put a bunch of references in this link. I should mention that there's a really nice tutorial by these authors on deep learning for inverse problems. And if you're interested in generative models, Alex DeMarcus has a really nice talk and from the Simons Institute, which is publicly available. I encourage you to listen to that. Thank you. I'll end it there.